So it's worth repeating. We understand that fully charged capacitor, no current, throw the switch, we get a current, and the inductor immediately starts pushing against that current. As the capacitor discharges, we build more and more current here. When the capacitor gets down to zero, there's nothing to build current anymore. The inductor is still pushing back against the capacitor, so that's going to drive the capacitor into an oppositely charged state, where you have the same charge eventually when the current finally reaches zero that you started with, assuming that you have no resistance. Now, in reality, we always have resistance, so we want to look at what happens if we put a resistance into this circuit. Okay, as promised, here's a circuit with an inductor, the same inductor we had in the previous example, the same capacitor, and a resistor this time. So, what's the equation that governs this? Well, as before, voltage drop across the inductor is L times second derivative of the charge with respect to T. That's the derivative of the current with respect to T, plus R times the current. The current is the rate of change of the charge on being transferred on the capacitor, the rate at which charge is being transferred on the capacitor. So that's R times dQ dt, R times I, voltage drop across the resistor, and the voltage drop across the capacitor is Q over C. Okay, and I used a fancy C here. I didn't use a fancy C here. Might be a good idea to make that change quickly. Hopefully I'm going to get them all. Okay. Now, how do we solve this equation? Well, this equation is very easy to solve. I'm assuming familiarity with differential equations. Let's divide through by L. I don't have a right side to fail to divide by L on. I do, but it's zero, so whether I divide by L over here or not, it's still zero. And I've had an epidemic of failing to divide the right-hand side. I don't know where that came from, but so can one person have an epidemic? Anyhow, we get this equation in a very straightforward manner, and we solve it. We assume that, I didn't write this down in class, but assume a trial solution, Q equals AE to the MT. Okay. I usually use R for the coefficient of T here, but since we have an R in the circuit, M is what's being used by the textbook that people on this campus are using. I think at the WCC campus we are using R, but it doesn't matter. This is very straightforward, and something you should be very familiar with at this point. Our characteristic equation is going to be M squared plus R over L times M plus 1 over LC equals 0, with solution written down, very straightforward, with the quadratic formula. We get negative R over L plus and minus. Well, I'm not going to read it to you. Look at that and make sure that's right, okay? Because if it isn't, we're in trouble. Now, the question that we're trying to answer here is, if this is a variable resistor, if we can set this resistance any place we want, for what values of the resistance does this give us an oscillatory solution? Well, you're going to get an oscillatory solution if this square root here comes out as imaginary. Okay, in other words, if the discriminant, the quantity under the square root sign, is negative. So we get an oscillatory solution if this is negative. Again, having had this recently in differential equations, which is my assumption, you've got to be very familiar with how that works. Okay, well, then we solve that, and that's going to occur. We just add the 4 over LC to both sides, and then we multiply by L squared. We get 4L over C. That's our R squared. Take the square root. Here's R. For the circuit that we have, I believe we get something on the order of 5.4 ohms. 4L will be 120 microhenries. C will be 4 microcoulombs. 120 divided by 4 is 30. Microhenries divided by microcoulombs gives us squared ohms. Taking the square root, we get ohms, and you can work out the details, and you should work out the details of that, of the units. Okay. Anyhow, the square root of 30 is about 5.4, so we get about 5.4 ohms. So if R is less than 5.4 ohms, our solution is going to have the form Q equals A e to the negative R over 2L times T times the cosine of omega T plus theta naught, where omega is the square root of the absolute value of what's under here. The I comes from the negative 1. So multiplying this by negative 1, we get this, and then the I comes out from the square root of negative 1. And I'm just waving my hands over that. That is, again, something you should be very familiar with. So there we have it. Now, we want to look at what this implies for the solution. First place, if R was equal to the square root of 4L over C, then these two terms would be equal and opposite, and we get omega equals 0. We would just then have an exponential decrease, A e to the negative R over 2L times T. Omega would be 0, so the cosine of this would be 0. If we make the assumption theta naught is 0, we just have our amplitude times an exponential, and we would just have a declining exponential. Now, if R is 0, what do we have? Okay, well, if R is 0, we just have the square root of 1 over LC. Now, you might want to refer back to your notes that I hope you took on the previous problem, the previous situation where we had just the LC circuit. We had no R. R was 0. In the LC circuit, we had omega equals 1 over the square root of LC, or the square root of 1 over LC. So we have that solution if R is 0, and that solution gave us an oscillation at constant amplitude and at some frequency. Okay, frequency being, well, the angular frequency being 1 over the square root of LC, and the frequency being that divided by 2 pi. Now, if R increases a little bit, okay, so we have R equals 0, that gives us our orange curve. If we have a small r that's greater than 0, also, I'll back up, if R is 0, of course, this e to the negative R over 2LT is e to the 0, which is 1. And again, that just gives us our oscillatory solution. Okay, if we have a small r but positive, then we are going to get this exponential decrease. So our amplitude is going to gradually decrease according to this exponential. If it's a small r, it'll decrease rather slowly. The amplitude will decrease rather slowly. The frequency of the oscillation is going to be affected because as r starts to increase, this number under here gets smaller. Okay, so omega, did I say the frequency is going to decrease? The period is going to decrease. The frequency, the angular frequency, is going to get smaller. It's going to decrease. The bigger r is, and the closer this is to 1 over LC, the less the angular frequency and the greater the period. So that the oscillatory behavior has a lesser frequency. Okay, greater period. The oscillations are going to be spread out more. They're not going to be as frequent as these, and you're going to have the exponential decrease. Now, if you let r get pretty close to square root of 4L over C, then you're going to have a situation where a larger r gives you a faster decay because you have a bigger number here, bigger coefficient, negative coefficient of t. It's going to drive the exponential function towards 0 more quickly, and you're going to have a period, you're going to have a period, a frequency that's approaching 0, a period that's approaching infinity. In other words, this thing is going to spread out much, it's going to get much we're going to have a much lower frequency, much longer period. I'm not sure what word I was fishing for there, but it never did come to me. Okay, so you're going to have something like this. So you can understand that as R goes from 0 to square root of 4L over C, you go from this behavior to this behavior to this behavior, and finally, as omega approaches infinity, as omega approaches 0, this term just drops off and you just have the pure exponential, and that's what's going to occur at the critically damped point. Now, if you go beyond that, because certainly you can increase R beyond that, you no longer have oscillatory behavior at all. You're going to have two exponential functions, one corresponding to the plus here, one corresponding to the minus. And that gets you into a different set of solutions that usually aren't particularly important, although in some cases they certainly are. I'll mention that I did these graphs kind of carelessly. I assumed in every graph that the initial charge was 0. Of course, an initial charge of 0, unless you already have a current running here, and of course it's possible to do that, but initial charge of 0 isn't consistent with the model that we've been talking about. And the charge should actually be some initial charge, and then the oscillatory behavior starts from somewhere up on the y-axis. And that does make a little bit of difference in how you look at these solutions. So I'll do that in a brief additional video clip.